This video is a product of the Annenberg Public Policy Center's Science of Science Communication initiative.
This is a story about curiosity leading to research and research producing huge benefits for the entire planet. Long before humans knew very much about the atmosphere, we were curious about the sky. Investigation of the air around us goes back thousands of years. Thunderstorms fascinated Homer in ancient Greece. In the Odyssey, Homer observed their sharp odor. He wrote, "The storm thundered and lightened, and the air was filled with sulfur." Homer didn't realize it, but he was actually describing chemical reactions that produce ozone. Ozone is a gas that has 3 atoms of oxygen in its molecule. It has a foul odor, and close to the ground, it is actually toxic. But lucky for plants and people and other living things, roughly 90% of the Earth's ozone is high in the sky, where it serves as Earth's sunscreen, protecting us from harmful UV radiation that comes from the sun. How do we know this? Because long after Homer pondered ozone in poetry, human beings began to investigate it through science. We've studied ozone on the ground, in the atmosphere, and even from space. And with this research, scientists predicted, found, and solved a dangerous problem with the Earth's ozone. Back in the 1880s, chemist W.N. Hartley was the first to figure out that ozone played a valuable role in the atmosphere. Ozone, he thought, must absorb some of the UV light as it passes from the sun through the Earth's atmosphere to us. In their day, Hartley and his peers could identify a few gases in the atmosphere, but most gas concentrations are so small, science didn't have equipment powerful enough to detect them. So the scientists got to work. In the 1920s, physicist G.M.B. Dobson invented a device that could measure small concentrations of ozone by recording the wavelength of light it absorbed. That pattern of light is called a spectrum, so Dobson called his machine a spectrometer. By 1948, Belgian scientists measured the infrared spectrum of air to show that another common gas in the atmosphere is methane. Every discovery made scientists more curious about the atmosphere, so they developed better and better tools. By the 1950s, they could measure 14 chemicals in the atmosphere. Analytical chemists continued to measure ever smaller substances, and today we can identify over 3,000 atmospheric compounds in the sky. Basic research made it possible for us to see what has been in the atmosphere all along. But it also revealed a serious danger. Here, let's go back to the ground. Since the 1960s, the world has seen a rise in malignant skin cancer that can be best described as alarming. Many factors have contributed to the rise: people moving and traveling to sunnier places, change in fashion over the years. We've literally exposed ourselves to more sun. But scientists also suspected that some of the Earth's sunscreen, ozone, would disappear. A decrease in ozone would let more of the harmful UV rays from the sun reach the surface of the Earth, and that would push rates of skin cancer even higher. But if the ozone continued to decrease, more harmful rays could also lead to an increase in cataracts, damage our immune systems, and make it harder for plants to grow. And the problem was getting worse, because as scientific discovery was advancing in the 1960s, so were other technologies much closer to home.
Wow, that door's got ice coming out of it.
Refrigerators preserved our food longer. Aerosol sprays made our rooms smell better. They made people smell better too.
When you're tense and rushed, it's time to try new Dial deodorant.
Styrofoam and similar products made things easier to ship or carry. And air conditioners made it possible for us to live in sunnier, hotter places. But in all of those things, we used a minute chemical with a very big name: chlorofluorocarbons, or CFCs for short. Okay, now look up again. As our ability to discover all of those chemicals in the atmosphere grew, In the early 1970s, British chemist James Lovelock detected CFCs in the air. He found them blowing east from big cities over Ireland, which made sense. More CFCs would be used in cities because there are more people there. So Lovelock put his detector on a ship and found CFCs in every one of the more than 50 samples collected in the North and South Atlantic. Lovelock concluded that CFCs from industrial areas traveled far and wide around the globe. All of these CFCs traveling in the air prompted future Nobel Prize-winning chemists F. Sherwood Rowland and Mario Molina to ask a very important question. What does it mean to have large quantities of CFCs in the atmosphere? First, these two chemists showed that at lower altitudes, CFCs could stay in the atmosphere for decades. They were virtually indestructible. But when they reached 18 miles above the Earth, harmful UV rays would break the CFCs apart into chlorine atoms and residual fragments. Other research showed that chlorine breaks ozone apart, forming chlorine monoxide. And that is part of a chain reaction that is absolutely devastating. A single chlorine atom can destroy 100,000 molecules of ozone. So every time a CFC compound broke apart in the ozone, the chlorine from it destroyed the Earth's protective sunscreen. And industry was releasing 1 million tons of CFC into the atmosphere each year. In 1974, Rowland and Molina predicted that, at that rate, atmospheric ozone would drop 7 to 13% by 2050. So they called for a ban of all CFCs. And just 4 years later, the United States listened to the scientists and banned the use of CFCs in aerosol sprays for hairspray, deodorants, and other products.
No.
Canada,
No.
Norway,
Nej.
and Sweden did the same. And then scientists discovered that actually, the problem was many times worse than they thought. At the end of the 1970s, British scientists, followed by Japanese and American researchers, showed that levels of ozone above the Antarctic were dangerously low, as much as a third lower than averages measured only a decade before. People all over the world began calling it the Antarctic ozone hole. Each discovery was another problem begging to be solved. This is atmospheric chemist Susan Solomon in Antarctica. In 1986, Solomon and several of her colleagues showed that elevated levels of chlorine monoxide in the atmosphere above Antarctica was causing the ozone hole. Flight data the next year proved them right. Chlorine monoxide from CFCs was devouring ozone above the South Pole. The evidence showed that the Earth had a problem, and the world responded. In 1987, 26 nations and the European Union signed the Montreal Protocol on substances that deplete the ozone layer.
All nations gathered here can be proud of what we have achieved.
They agreed to limits on the production and use of gases that deplete ozone. Besides CFCs, these included methyl chloroform used in solvents and bromine chemicals from fire extinguishers and pesticides. It called for a complete ban on CFCs in developed nations by 1996, and today all 197 members of the United Nations have signed it. It is the very first international treaty to achieve such unanimity. Without the treaty, by 2060, 2 million more people each year might have gotten skin cancer, and entire ecosystems could have been damaged due to the loss of up to 60% of the ozone layer. But because of the Montreal Protocol, industry identified and produced chemicals with safer properties, and today, humans use 80% less of the substances that damage the ozone layer. So world cooperation based on scientific data is actually restoring the Earth's ozone. Ozone is coming back. Basic scientific research and the pure joy of discovery identified one of the Earth's most urgent problems and offered the world a solution. Science works. Now that's poetry.